Hello everyone, today we're going to be taking a look at another recursive type of brain teaser that is Quantibus number 11, and I was actually asked this exact question word for word in a live interview with Jane Street a few months ago, so it's certainly a relevant brain teaser. And the situation basically is you and a friend are playing this game in which you take turns multiplying a number. The game begins with the number 1, and on each turn, a player must multiply the current number by some integer between 2 and 9 inclusive. The first player to make the number reach or exceed 5,000 wins. So would you rather go first or second to guarantee a win? So let's just do a quick example run just to understand what's going on. Basically, we start with the number 1, right? And whoever goes first is going to multiply it by some number between 2 and 9 of their choice. So let's say they choose 9, and now it's the other person's turn, and they get past the number 9, and then they can choose to multiply it by their own number between 2 and 9. So let's say 2, and the number would go to 18, and it would get passed back to the first person, and then this would go on, everyone multiplying the number until whoever multiplies the number, let's say it gets to 4,000, and they multiply it by 2, then it gets over 5,000, and whoever did that would have won the game. So now to answer the question of would you rather go first or second to guarantee a win, it's pretty helpful to start from the base case in this situation, or what we know, which is that you have to get it to 5,000, and we're going to kind of work our way backwards until we understand who wants to go first. So let's just say we have the number 5,000 over here, and we can just use 4,000 again, right? If we get past 4,000, we automatically know that we win no matter what we do, right? We can multiply by any number between 2 and 9, and we're going to win no matter what. So obviously there is some range of numbers here such that we have a guaranteed win going back before 5,000. Let's say we get past 1,000. Can we still win by multiplying by 2? No, but we can win by multiplying by 9. So there still exists a number that we can win with. And now we basically have to find the cutoff point. So basically the number such that even when we multiply it by our biggest number, which is 9, it still doesn't guarantee us a win, and it'll go before 5,000. So to do that, let's just divide 5,000 by 9. And there's a really simple trick for dividing things by 9 if you don't know. Basically, we just keep kind of a running sum as we go through this number, and we kind of bring the numbers down. I'll just show you what I mean. Basically, it starts with a 5, so we have a 5. Then we add 0, right? So now we still have 5. And then we add 0 again, so we still have another 5. And once you get to the end, you take the sum as a remainder. So 5 plus 0 is 5 again, and our remainder is 5/9. So this is 5,000 divided by 9. And now we know that basically if we have 556, if we multiply that by 9, that's going to be greater than 5,000. But if we have 555 and we multiply by 9, that's going to be less than 5,000. So 556 is a winning number. If we get past that, we know we have a guaranteed win. This is kind of like a win range, all these numbers here. And if we get past 555, then we are going to lose. And that is because no matter what we multiply 555 by, it's going to go somewhere in our opponent's win range, and then they're going to have a guaranteed win. So now the question becomes, what are all the numbers that force our opponent to pass us some number within this range? And just to formalize that, basically we're going to have this range. Let's call this x, and let's say, what is the number x such that for all m in this range, 2 to 9, these are all the numbers that they can multiply by, then x times m is going to be greater than or equal to 556. So we're saying xm, we want that to be greater than or equal to 556, and we're saying for all m, because we're trying to force our opponent, right? So no matter what number they multiply by, we want it in our win range. So for all m, so that means we're going to look at our smallest possible number 2 and say, even if they multiply that number by 2, we still want it to go in our win range. So now we're looking at 2x greater than or equal to 556, and you can divide 556 by 2. We're just going to divide it digit by digit. So 250 plus 25 plus 3, that's going to be 278. And this gives us the bottom end here. So now we know if we pass our opponent 278, no matter what they multiply it by, if it's 2, it's going to be 556. If it's greater than 2, it's still going to be in our win range. So we're going to win no matter what if we pass our opponent a number within this range, because they're forced to put it in our own win range. So now the new question becomes, how do we pass our opponent a number within this range so that they pass us a number within our range, winning range, and then we win? So let's look at 277 to start, as that's one below this number. And we know that if we multiply multiply 277 by 2, it's going to be 554, and that's going to be in their losing range, which is what we want. And we want to find the bottom end of this range, so this x. And notice that basically, if we formalize it, we're just saying, instead of for all m, since it's our turn and we get to choose a number, we just want to say find x such that there exists an m within this range, such that when we multiply x by m, we get it into this range, right? Greater than or equal to 278. And basically, since we're doing there exists, we want to use our biggest number to get the lowest possible end of this range. And so we're going to end up dividing 278 by 9 again. And if we use the trick from before, basically what we're doing, we bring the 2 down, we keep a running sum, 2 plus 7 is 9, and we still keep a running sum, but we're at the last digit, so 9 plus 8 is 17, and we take that as a remainder over 9. So 29 and 17 ninths, that's just 30 and 8 ninths, and that's 278 divided by 9. So now we know that if we have the number 31, we can multiply it by 9, and it's going to be greater than 278, and instead, if we get the number 30, it's going to be less than 278. It's going to be 270, and that is not what we want. So this is the end of our win range, another win range here. So now you can kind of see the pattern emerging. Basically, we want to force our opponent to pass us a number within this range. So we're going to do this whole thing again. 30, obviously, they have to pass us a number no matter what they multiply by. If they multiply by 9, it's going to be 270. It's going to be in our win range. If they multiply by 2, it's going to be 60, also in our win range. And we want to find the cutoff point again. So we're basically going to say, even when they multiply by their smallest number 2, how can we get it to be still in our win range? So x, let's find x such that x times 2 is greater than or equal to 31. So 31 divided by 2 is 15 and a half. So we want x greater than or equal to 15 and a half. So since we're only dealing with integers, it's going to be 16. So if our opponent has a 16, even if they multiply by 2, it's going to go into our win range, which is what we want. So now, just like before, the question becomes, how do we pass our opponent a number within this range so that they lose? Well, we look at 15. If we multiply by 2, it's going to go into this range, which is what we want. And now again, we want to find the lowest possible numbers such that when we multiply it by 9, it's still going into our opponent's losing range. And to do that, we're going to take 16 and we're going to divide it by 9, which is, you don't have to do this for that. It's just going to be 1 and 7 ninths. So basically 2, because we're only dealing with integers. Let me erase this. And so if we get past the 2, we're going to multiply by 9 and it's going to go into their losing range. So this again is a win range, and we've recursed all the way back down to 1, which is where the game started. So basically we understand that 2 to 15 is a winning range. So 1 must be a losing number, because no matter what our opponent multiplies 1 by, or whoever's playing the game, no matter what they multiply 1 by, it's going to go into the win range of the other player, right? So 1 is a losing number. And the final answer will be, would you rather go first or second? You'd rather go second. So now finally, maybe let's just go through one example just to see what's happening fully. Basically, we have deduced that we want to go second. So let's say our opponent is going first. They're going to start with the number 1. Let's say they multiply it by 9. They can multiply it by whatever number they want. It's still going to go into our win range. And now that we get past the number 9, we want to put it into this losing range. So we're going to multiply by 2. It's going to go to 18. They can multiply by whatever number they want. Let's say they multiply by 2. Now it's going to 36, which you can see again is in our win range. And if we get past 36, we want to get it into their losing range now. So for 36, we're going to multiply that by 9, and that's going to get it in here. It's going to be 324. And now our opponent can multiply by whatever they want. It's still going into our win range. Let's say they multiply by 2, then it's going to be 648, and we can multiply that by 9, and it's going to be greater than 5,000, and we're going to win. So you can see that's how it works. We're basically, when it's our turn, we want to force it into our opponent's losing range, which we calculated, and when it's their turn, they're forced to put it back into our win range. So it's guaranteed win if we go second, we play optimally.